So today we're going to begin a new unit on light. And in this chapter, in this lesson, we're going to look at fundamentals of light. So let's take a look at our objectives. First, describe the different models of light. Understand that light is an electromagnetic wave. Describe the relationship among light, radio, micro, and X-rays. Then we'll solve some problems involving the speed of light and the wave equation. And finally, be able to contrast what happens to light when it hits different medium that might be opaque, transparent, or translucent. So early concepts of light, some thought light consisted of tiny particles which entered the eye. So early Greek scientists looked at an apple and said there must be some tiny little particle of the apple that reaches our eye. That's what allows us to observe it. Others say, no, it's a streamer that comes out of our eye and touches on the apple, and that's what allows us to observe it. Well, it turns out they were both right. Light behaves both as a wave, and this was first defined by Christian Huygens, who published his wave theory of light in 1690, that light behaves as a wave. And it also behaves as a particle. It has this dual nature to it. And the particle behavior was first defined by Albert Einstein in his theory of photoelectric effect in 1905. And the name he gave to a particle or small packet or unit of light is the photon. So we'll be talking in this unit about both behavior of light as a wave and behavior of light as a particle. Both can be useful for describing how light behaves and some of its properties. We're going to use a ray model to introduce the way light travels and interacts with different objects. So whether it's a light as a wave or light as a particle, the ray model is useful for us to describe its path and any changes to its direction. So let's look at a couple examples, right? The ray is basically an arrow, represents a narrow beam of light. So you could kind of imagine an infinite number of narrow rays, right, that are traveling in the same direction from the light source to what it's shining on. We can show a property of reflection, right, with a light ray where the light bounces off an object. We could also show the property of refraction. This occurs when light hits an object and it slows down as it passes through it and then speeds back up again on the other side. That causes it to change direction, which is known as refraction. We will be taking a deeper dive into refraction here in a future lesson. Now, light is an electromagnetic wave. It's emitted by the accelerating electrical charges, and typically these are the electrons. So as electrons speed up and then slow down, as they slow down, right, they're going to have less energy. Well, that energy is created as light energy that's given off by the accelerating electric charges. So an example is an old-fashioned light bulb, right? It has a tungsten piece of wire through it. And as it heats up, based on the electrical current flowing through there, it causes the electrons to accelerate. And as they accelerate, they create a light wave, okay? So we get electromagnetic radiation or electromagnetic wave being emitted by those accelerating electrons. Now, an electromagnetic wave has two parts to it. The reason we call it electromagnetic is that it's partly electric and partly magnetic. So imagine our accelerating charge, right? Moving back and forth, oscillating here. It's going to create an electric wave in one direction and a magnetic wave in the other. The electric wave and the magnetic wave will be at right angles to each other. So if you could imagine kind of two pieces of paper, right, two planes that intersect each other, the electric wave is traveling in one sheet of paper, the magnetic wave is traveling in the other. And it might look something like this. Okay, now the arrows represent changes in the electric field strength or magnetic field strength. Now, we haven't studied electric fields or magnetic fields yet. We'll get into that before the end of the year. But it's the variation in that field strength that creates this wave. So here's a little animation that helps to contrast, right, a mechanical wave, such as a vibrating string, which we've been studying, versus an electromagnetic wave. Now, the first thing you can see is that they are both transverse waves, right? The motion of the medium in the mechanical wave is perpendicular to its direction of travel. And in a light wave, the variation in the electric field strength or magnetic field strength is perpendicular to the direction of the wave. So they're similar in that they're both transverse. They're different in that it's the variation of the field strength rather than actual motion in the medium. All right, let's talk about the electromagnetic spectrum. Okay, what is it that allows us to actually observe a light? It turns out that visible light is just one part of a range of frequencies of electromagnetic waves. It's just one very narrow band that we can actually observe with the human eye, but other waves, as we'll see, are exactly the same. They're electromagnetic waves. So the visible light is just a very narrow region. And this chart will fill out, we're going to show the wavelength. So you can see the wavelength of visible light is very short, right? 10 to the negative 7th meters. That would be like 1/100000th of a meter long, the light wave for that. And within that visible light range, right, we have kind of the spectrum of colors going from red to orange to yellow, the green, the blue, to turquoise, dark blue, and violet. Those are the colors of the rainbow, so to speak. And as I said, the wavelength of visible light is about the size of like single-celled organisms, right? A few billionths of a meter in length. Now, if we go to the left of that, right, these are going to be longer wavelengths. The next portion of the spectrum is the infrared portion. So infrared light is the electromagnetic radiation that's typically given off by heat, so like a fire or a candle flame. It's not visible. A lot of the remote controls that we use with our electronics use infrared frequencies, so we can't actually see the beam as it travels across the room to the TV set, but it's there nonetheless. And then as we get longer wavelengths, we get into microwave frequencies. So these are radio waves that we use for communication. The higher frequency radio waves are considered microwaves. It's also the same radiation that's used in your microwave oven. And then we move into lower frequency radio waves. So this would be like our FM radio or AM radio in our car as we drive around. And now you can see the wavelengths for a radio wave are in the order of a kilometer, right? So there the waves are as large as, say, our tallest buildings or skyscrapers. Now, if we go the other direction, we get into ultraviolet radiation. So these are even shorter wavelengths than visible light. And the size of these starts to get down to a, say, the size of a virus, or down to the size of actual molecules, right, of different atoms linked together. And then we move down to the X-ray. So these are getting shorter and shorter wavelengths, higher and higher frequencies. So X-rays, you may have already had a X-ray, right, at the medical office. It's still electromagnetic radiation. And then the highest is what we call a gamma ray. And these are created in our solar system. Often they're generated by the reactions going on within the sun. Generally, the shorter the wavelength above the visible light, so ultraviolet, X-ray, and gamma rays, are harmful to living things. Those electromagnetic waves at those short wavelengths are capable of damaging the cells and structures of living things. So humans try to avoid ultraviolet, X-ray, and gamma ray radiation. That's why when you go get an X-ray at the dentist or the doctor, they cover you up with a big lead sheet, and the operator does not stay in the room, right? We want to have just very small little doses of X-rays when we have our images taken. All right, speed of light. Now, you've probably all heard that the speed of light is like a speed limit, right? Nothing can travel faster than the speed of light, and that's true. But why is it so difficult to actually measure the speed of light, right? Can you think of a practical method to measure it? In other words, it would be pretty hard, right, for someone to stand at the other end of the room and flash a light and say, go, and then you're at the other end with a stopwatch, right? I mean, in our normal world and distances, light seems to be instantaneous in terms of the time it takes to reach one point to another. So this is a challenge. How do we measure the speed of light? Well, it was first done by a physicist named Albert Michelson back in 1880. He won the Nobel Prize for this in 1906. Now, how did he do it? Well, it was kind of an interesting setup. He took a 8-sided rotating mirror. So picture the sides of the mirror here, the hexagon or octagon rather, being a shiny reflective surface. And he took a light source. Now I'm showing this as a laser, right? Back in 1880, you didn't have light sources. He had oil lamps with lenses on it that could focus that light beam. And then he had another mirror up on a mountain that was about 35 kilometers away. And then he had a detector. And what he did was shine the light. It reflected off of the 8-sided rotating mirror, hit the mountain, came back and hit the mirror, and then into the detector. And the mirror was actually spinning, right? So based on the rate at which the mirror was spinning, in order to achieve a full reflection, right, to the mountain and back to the mirror and into the detector, he was able to calculate what the speed of light was. So he figured out the round trip was 70 kilometers. The rotational speed in which it would be able to fully reflect it was about 32,000 revolutions per minute. So the time for 1/8 the revolution, right? You got to think of that, just one side of that octagon has a reflector on it. So it has to hit that same surface. So the surface had to turn 1/8 of a rotation to catch the reflection from the mountain. That took about 2.3 times 10 to the -4 seconds. So if you add all that up together, he came out to about 299,000 kilometers per second. So good job, Albert. You won a Nobel Prize for that. Now, that was over 100 years ago, and the number was very close to what we use today as the speed of light, right? 299,792,458 meters per second. Now, for the problems we're going to do, we're going to round that off to just 3.0 times 10 to the 8th meters per second for our calculation. Okay, so about 300 million meters per second. And we use the small c as the symbol for the speed of light. Now, you might have heard of this unit of measure that astronomers use. Is called a light year, right? How far does light travel in 1 year? Well, let's figure it out. If it travels 3 times 10 to the 8th meters in 1 second, then how many seconds are in a year? Well, we know there's 3,600 in an hour, and then 24 hours in a day, and then 365 days in a year. So if we multiply all that together, right, remember using our unit analysis, we get about 9.5 times 10 to the 15th meters per year. Now, maybe in miles, that makes a little more sense to us. So if we convert it, we get 6 trillion miles that light will travel in 1 year. So that gives you a good feel for how big our universe and our galaxy is, right? The nearest star to Earth is 4 light years away, so 24 trillion miles away. Now, we can also use the light speed to kind of do our normal calculations around speed and distance and time, right? How many minutes does it take for the sun's light to reach the Earth? And let's use an average orbital radius of 1.5 times 10 to the 8th kilometers. So that's the distance the Earth is from the sun. We divide that by the speed of light, and we get about 500 seconds, or a little over 8 minutes. So the light we receive from the sun is about 8 minutes old. If the sun were to all of a sudden burn out, right, it would take us about 8 minutes before we would notice it. All right, now the speed of light is not a constant, okay? Now, there is the speed of light that we've been talking about is the speed of light in a vacuum, or very, very close through normal atmosphere, okay? But light can actually travel slower, and it does when it moves through a medium that is what we call non-resonance, okay? In other words, as it moves through a medium, bouncing off one atom or molecule and then rebounding off another, it winds up taking a longer path to get through that medium than if it were traveling through a vacuum. So light travels with a speed that is less than the speed of light in a vacuum when it's traveling through other medium. So here's some examples of that, right? And we calculate it based on a percent of the speed of light in a vacuum, right? So in a vacuum, the speed of light would be 1 times c, or 100%. You can see it slows down a tiny little bit in air, but then as we get into water or glass or quartz or diamond, right? These are transparent materials that it'll travel through, but it slows down significantly. Look at the diamond, how dense that is. Light travels only at about 40% of its normal speed as it travels through a diamond, okay? So think of light as maybe an upper speed limit in the speed, but in many situations here on Earth, light is actually traveling slower than that. All right, let's do a couple quick calculations here using our wave equation. Find the wavelength of red light in a vacuum with a frequency of 4 times 10 to the 14th hertz. So if we want to find the wavelength, we're going to divide the speed of light by the frequency, and we do that, and we get 7.5 times 10 to the negative 7th meters. Now, when you do these calculations, you'll want to use your calculator in scientific notation mode, because we have very large numbers for frequency and very small numbers for wavelength. Let's do another one where we want to find the frequency, and we're given the wavelength. So we would divide the velocity by the wavelength, and in this case we would see we get a frequency of about 7.9 times 10 to the 14th hertz for violet colored light. All right, so what allows light to pass through some medium like glass and not through others like wood or stone? Well, it depends on two things: the frequency of the light and the natural resonant frequency of the electrons. So when light hits an atom or molecule of a particular type of material, it can cause that to begin to oscillate, right? And if the light frequency matches the natural resonant frequency of the object, we get resonance, okay? Now, if it doesn't resonate, then often that extra vibration there is just generated as heat, right? So light strikes an object, we've all experienced that. We can feel it warming up when it's in the sunlight. Okay, so light is absorbed as heat when it's excited at its natural frequency. When it is re-emitted, or light is re-emitted when not excited at its natural frequency. So if it doesn't match, then it just kind of passes right on through the material. So let's look at some examples of that. The first is opaque. This is media that does not transmit light, but reflects some light, okay? So a block of wood, right? The light shines on it, and it reflects or absorbs all of that, okay? So it reflects a little bit because we can actually see, right, the color and texture and pattern of the wood, but much of the light is absorbed. Opaque materials can also reflect a large amount of light. So shiny metal surfaces, right, like the backside of a mirror, a silver mirror, will reflect, say, 80 or 90% of the light that hits it. Another type of media property is called transparent or transparency. And this is where the light travels through and gets re-emitted, right, from kind of atom to atom, molecule to molecule, and comes out the other side. Now, it may slow down as it goes through that process, but the majority of the light passes right through it. Now, again, it depends on the frequency. Ultraviolet light, right, as it passes through some material and it resonates, most of that light winds up in the form of heat. So the most common example of this is common window glass. It lets visible light through, but it actually blocks ultraviolet waves. So it's transparent to visible light, but natural glass is opaque to ultraviolet waves. That's why when you're driving in a car, you have the window down, right? You can get a tan or a sunburn on your arm. If you roll the window up, it protects you from those ultraviolet waves. And then the last property here is translucent. This is media that transmits some light, but does not permit objects to be seen through them. It kind of scatters the light. So we get some neat effects often for translucent materials. All right, that's it. So we know how to describe the different models of light, wave and particle. We understand that light is an electromagnetic wave. We understand the difference in the spectrum of visible light, radio waves, microwaves, X-rays. We know how to use the speed of light and the wave equation to solve problems. And we looked at properties of medium, opaque, transparent, and translucent behaviors. All right, that's it. Take a look at the assignment.